Hi, everyone. My name's Kristen Fletcher. I'm the Adults Program Coordinator for the Hailey Public Library, and I'm delighted to welcome one of opening back up. Right now, the drop box is open for returns Monday through Friday, 10 to 2. And then stage 2, we're tentatively planning to open for limited services starting May 1st. Again, it's Monday through Friday, 10 to 2. We'll have a table set up in the foyer. People will be able to pick up interlibrary loans, holes that they've been waiting for, and we're also accepting new materials requests via our website. We are certain to follow all safety guidelines. We've been talking about this a lot. Just check our website for the actual date. We're planning on it, like I said, May 1st. But if things change, then we'll be flexible and change with that too. I wanted to mention a couple of classes that are coming up. Next Wednesday, we have season extenders for the garden with Manon Gaudreau. You can find out more information on our website for that. And then May 6th, we're bringing back astronomer Tim Frazier for a 4-part series on astronomy. The first talk is Our Place in the Universe. So if you've ever wondered how we fit into the big scheme of things, Tim will show you wonderful images and great stories. He's a wonderful educator, a wonderful teacher. So before I launch into tonight specifically, I wanted to give a big shout out to 2 people. First, Paul Reese, who attended a field trip at the Idaho National Laboratory and came back and emailed me immediately and said, hey, the INL is doing some wonderful work. You should get some of these folks over here for some talks. And so he connected me with another wonderful person, Abby Todd Bloxam, who has been my main contact. They have a 7-person team that I've been working with, and she's been my main contact through this. And it's really been wonderful. They've been warm and welcoming and just as easy as could be to work with. So I did want to say that tonight's talk is the first of 3 that we're planning. The next will be sometime in the summer. It's about a self-contained power systems called a microgrid, and it's useful for remote areas like our valley. And then later in the summer, we're going to be celebrating with the INL with a space party to celebrate the landing of the Mars rover Perseverance and the role that the INL had in powering that spaceship, I guess you call them spaceships, to get it to Mars. So those should be great talks. And there'll be a little bit of time at the end of our presenters' talk tonight for feedback. How did this work? How was registration? How was the talk? Just any kind of feedback you'd be willing to give. And we're also interested in any other kind of topics where we might partner with the INL or other organizations. So there'll be that opportunity in a little bit. Our presenter tonight is Lee Walker. He is a battery engineer at the Idaho National Laboratory. And just to let you know that you're all muted and the video feature has been turned off. But to make sure that the evening is as interactive as possible, please put any questions in the question box. It works just kind of like a chat. There'll be a place to type things in at the bottom, and we'll be monitoring those questions throughout Lee's talk. We'll try to get as many of them answered as we possibly can. Let's see, I just want to make sure that, the talk is going to be recorded, and a link to the talk will be sent out after the event, a few days after the event. So let me introduce Lee Walker. Like I said, he's a battery engineer at the Idaho National Laboratory in Idaho Falls. He earned his bachelor's degree in electrical engineering from Northern Illinois University and a master's in power engineering from Illinois Institute of Technology. Before joining the INL, he worked at Argonne National Laboratory for 10 years, testing batteries and fuel cell performance. At the INL, Lee analyzes the life, and performance capabilities of batteries and is a lead in INL's Energy Storage and Advanced Transportation Department. So please join me in welcoming Lee Walker.
Thank you, Kristen. So as she said, my name is Lee Walker. I'm the group lead for the Energy Storage and Infrastructure Group within the Energy Storage and Advanced Transportation Department at INL. So and tonight we're going to take a look at future of charging for electric vehicles. So Idaho National Laboratory is one of 17 of the Department of Energy's R&D laboratories. We are, so INL is made up of two main locations. We have our site out in the desert, and then we have the facility, the research and education campus, which is inside Idaho Falls. And that's actually where I do the majority of my work. Actually, all of my work. So INL's vision is we will change the world's energy future and secure our critical infrastructure. We do this through the development of not just nuclear power, but also through doing development of grid stability and security, biofuels, and advanced vehicles and transportation applications. So INL has been doing transportation and battery research since 1983. So we stood up the Energy Storage Testing Laboratory in 1983 to be able to do testing of full-size electric vehicles, batteries, in support of the Department of Energy's electric and hybrid electric vehicle programs. So in 1987, Idaho team initiated the management of the DOE Site Operations Program, which included 13 electric industries, government, and university partners conducting on-road and on-track testing of electric drivetrain vehicles. In 2002, initial testing activities of the neighborhood electric vehicle, which are four-wheeled vehicles defined by the National Highway Traffic Safety Administration as subject to Federal Motor Vehicle Safety Standards, number 500. In 2003, we partnered with the Arizona Public Service Utility to create the first hydrogen production and dispensing stations in the United States to support testing of internal combustion vehicles to operate 100% hydrogen and blends of hydrogen and compressed natural gas. One of our bigger activities was from 2011 to 2015, INL collected and analyzed data from 124 million miles of driving and 6 million charge events over a period of 3 years, providing the most comprehensive view of light-duty plug-in electric vehicles and the charging usage to date. And then 2014 to 2016, INL researchers worked with 6 companies to conduct bench testing of wireless charging systems. Results supported the SAE's, the Society of Automotive Engineers International Wireless Charging Guidelines, published in 2016. So we have a strong history in nuclear power research, and this helps us to understand the complex systems and the power engineering. And these types of systems, and as I'll go on later on in my talk, there's a broad interaction between all the different systems, be it a vehicle all the way to the grid, and there's a significant interactions with all those. So today's advanced transportation and energy storage research. So we've got several main topics that I'm going to go into. Feel free to ask questions whenever you want, and I'm definitely not going to be able to hit all of our areas, so definitely ask questions if there's something that you would like to know more about. So as Kristen kind of said, my actual area of research is in batteries. So the batteries, the main areas that we focus in is life and performance testing at INL. But we've actually have programs that develop everything from materials level research, which is looking at one of the main programs we have right now is developing 500 watt hour per liter, or sorry, 500 watt hour per kilogram batteries. To give a perspective, the current state of the art battery that you would find in a vehicle is about 270 watt hours per kilogram. So this is a significant increase in the energy density for the batteries, which would result in significantly higher range, hopefully lower cost because you could have a smaller overall battery and still achieve high range. The other areas that we do a lot of work in is grid impact. So how do we look at charging events? What happens when we start getting broader acceptance of electric vehicles in the market? What happens to what happens to the utility, the stability of the grid? What happens if everyone wants to charge at the same time? And what happens when we start implementing the next generation of electric vehicles, which will be able to enable extreme fast charging, which is where we could charge 80% of a vehicle's range in 10 minutes or less. And then another thing we'll go over is charging stations. So work that we do is, where do we put these charging stations? What type of charging station should it be? At what rate should it be able to charge? And those types of applications. So real quick, I was going to give we have actually online a virtual tour of our electric vehicle and infrastructure laboratory. So let's see if this pops up. So here we can see our electric vehicle and infrastructure laboratory. This laboratory has two main sides to it. So we have the conductive charging side. So this is where all the plug-in vehicles go. So here is a bunch of, these are all level 2 chargers. So these are the types of chargers that you'd find at grocery stores a lot of times. You would install in your home. You can install at a level 2. And then, oops, sorry, moving around on me. Then we also have this big white box here. That's what we call a DC fast charger. So that's able to charge at a 50 kilowatt rate. So to give a perspective, most electric vehicle batteries are somewhere between 50 kilowatt hours and 100 kilowatt hours. So this would charge it fully in 1 to 2 hours, whereas the other ones are less than half that. A level 2 charger does not exceed about 19.2 kilowatts. On the other side, over here, we have our wireless charging area. So, so this is our wireless charging setup. So below the car here is what we call the ground coil. The ground coil is what's actually hooked up to the grid. Then attached to the car, is the secondary coil. The secondary coil is positioned over top of the ground coil, and we then are able to wirelessly transmit power between the two coils to be able to charge the vehicle. So a ground coil could be embedded into the floor of your garage. It could be put into parking spaces. And we actually even have research of working on what we call dynamic wireless charging, where we would actually embed these into the road surface, and you could charge as you drive down the road. So charging speed. So I kind of alluded to that just a minute ago. So there's multiple types of chargers. So we've got level 1 chargers, which are going to be what's embedded into your actual vehicle. Those are going to take usually in excess of 8 to 10 hours to fully charge a vehicle. Sometimes more, depending on the size of the battery in the vehicle. Then we're going to have level 2. Level 2 chargers will take somewhere between 4 to 6 hours to fully charge a vehicle. Then there's going to be the DC fast charger, which is going to be about an hour, sometimes less. And then then auto manufacturers are actually starting to look at higher and higher levels of charging. So the next thing to come out is the extreme fast charger. And so that's kind of a picture of what you see here. And we actually have it hooked up to an all-electric bus. These extreme fast chargers will charge anywhere between 5 to 10 minutes. They are 350 kilowatt output. So 7 times higher than the regular DC fast charger. So it's a significant load. This is not something you would actually install into your garage unless you have a very large power feed going into your home, and most of us don't. So they would be able to charge. So a lot of auto companies are looking at batteries that are 800 volts and be able to charge in excess of 500 amps, which is quite a significant amount. So I see someone has a question about does extreme fast charging shorten battery life? The answer is we're studying that actually. So there is definite signs that it can, but it very much depends on the design of the battery. How thick are the electrodes? What are the materials of the battery? That will actually dictate what the life of the battery is. And there's also indications about how fast do you charge. We can charge at we can get almost up to that 4C rate, the 350 kilowatt rate, and not cause significant degradation. If we start to exceed that, then we will start causing a phenomenon called lithium plating, where you actually plate metallic lithium onto one of the electrodes, which is not what you want to do. You want the lithium to stay as ions. So the other area that we worked on is actually working in standards to be able to look at different types of charging connectors. Obviously, there's going to be some difference related to what type of power are you charging. But there are 3 main types of connectors out there. There's CCS, CHAdeMO, and Tesla. So all 3 of them are different. They're not interoperable. You can't actually just take one of these and retrofit it to be able to fit to your vehicle. Some chargers, like that DC fast charger that I showed, actually has 2 of the 3 plug styles on it, so that way you can actually use that. And this is only really a big problem if you're out and about and want to be able to charge your vehicle at some other point. If you have your vehicle at home, obviously you're going to have a charger that is going to be specific to yours. And then Tesla decided to do their own type of charger. So the other areas.
Excuse me, Lee. Somebody had a question when you were talking about a wireless charging, and they said, could there be some kind of danger? Like, you know how cats and dogs like to get underneath your car? Could that be any kind of danger to them?
Yeah, so that's one of the areas of study. I should have pointed it out while we were looking at it, but we actually go through and measure the electromagnetic field all around the charger to make sure it's within safety standards. There is danger associated with, for instance, so there's always the discussion about, well, what happens if my cat falls asleep on the coil? Because it's a nice warm, it can be a nice warm place. And for the most part, it won't hurt the cat. And more than likely, the cat would move before it would actually cause any serious injury. But yeah, we're definitely, we look at that type of implication. Another area where we're actually doing work in is active field cancellation. So I'm trying to make sure that the field is all directed into one small space where the two coils are, and doesn't go outside of that space. Because one of the bigger concerns is actually not like an animal going to sleep on the coil, but what happens if someone with a pacemaker or an implanted medical device walks too close to one of these, when they're, especially the high power versions. So we're studying that, and there's standards out there that say this is the field at this distance needs to be below a certain level. And we do all those types of measurements to try to qualify, yes, this is actually something that is safe, or it's not. And we need to implement something like active field cancellation.
Okay, great. Thanks very much.
Mm-hmm. So the other aspect about charging, so one of the areas that is of concern with charging is, well, what happens if we start all of a sudden, lots of people buy electric vehicles? Probably the most common charging time would be everyone gets home at night after coming home from work, plugs their vehicle in, and all of a sudden you get this high demand, and it could cause at least a localized failure within the grid. Well, there's areas of research and interoperability studies that we do to try to understand what are those dynamics. How can we mitigate those dynamics? We actually have a program called Behind the Meter Storage, which would utilize large stationary batteries to help act as a buffer to the grid. So that way, if there were a sudden demand, those large stationary batteries would be able to take up the demand while the power company increase their output, and it would give the power company time to actually get that output turned off. So more onto wireless charging. So as I described, so I had mentioned that we do the field measurements. So if you look in the picture here, right behind the vehicle, there's a little white sensor that's on a boom, and that's actually our field measurement probe. So, and we'll move that all around to be able to see where what the field level is at different points. What is the field level if we start moving into misalignment conditions? So that there's a certain alignment that is needed for optimal power transfer, and that alignment and distance between the two coils is designed specifically for a vehicle. But what happens if those aren't perfect? Well, you start getting, you of course don't get optimal power transfer, so you won't get as much power into the vehicle as what you are transmitting. So you get an overall loss of efficiency. And we do those types of studies is, well, how much energy are we putting into the ground coil versus how much energy is actually making it to the vehicle? If we were to increase the distance between the two, and something you can't see in the picture is the coil that's on the ground is actually on a lift table that we can move it up and down. We can also move it side to side and front to back to be able to adjust alignments to see where the optimal point is. Has this been optimized, and what is the efficiency if we start moving this coil around? And then we also are doing a lot of this testing to help inform the Society of Automotive Engineers to be able to set standards for automotive manufacturers and wireless charging manufacturers. So kind of the next thing we look at is what is the impact on the actual electrical grid? So we're looking at a potential increase of the electric vehicle market from 5 to 20% of the nation's electric utility utilization. So that is actually a pretty significant increase, and for something that has been relatively constant for the electric utilities, all of a sudden they're going to see this increase between 5 and 20% onto their load. So what is the implications of that? So, and what are the implications of people actually plugging vehicles in at different times, and what will that affect the overall stability of the grid? So the picture you see here is on the left side is our electric vehicle infrastructure laboratory. So you can see the charging, the conductive charging here in the foreground. In the background is the wireless. Then on the other side is our microgrid and our grid simulator setups. And so what those do is we actually have those two facilities, the electric vehicle infrastructure lab and the microgrid and grid simulators hooked up together. And so that way we can actually have actual hardware and see what actual hardware does if we start having instabilities in the grid. And we can also then simulate additional. So we have a handful of chargers there, maybe 5, but what happens if that was a 100 or 200 vehicles? So, and we actually simulate additional vehicles on the grid in our grid simulator. The other aspect that we look at is, well, how secure is this?
A quick question. Is the electricity stored in some way before it's delivered to a car? I mean, if you want to plug in a lamp, you just take the cord and plug it in, and that energy is it's coming over the wires. It's not stored anywhere. You just plug it in and the light comes on. So is it the same sort of thing with charging electric cars? You just basically plug it in. There's no storage feature.
Right now that's the case. Is pretty much it's on-demand usage. There is a lot of work, and we're looking into that. And actually, attached to the microgrid, just on the other side of the wall here, we've got a large stationary flow battery that we use as grid storage. So there's a lot of effort going into studying and implementing grid storage. And then that is one of the programs I mentioned was behind the meter storage. That is going to be on the consumer side of the meter. And then that will help enable storage for charging facilities. One of the areas that we're directly looking at within that program is putting a 1 megawatt hour to 2 megawatt hour stationary storage. So it's pretty significantly sized battery to be able to enable extreme fast charging. If we're doing extreme fast charging, let's say we have 10 350 kilowatt chargers and they turn them all on at once. That's now 3.5 megawatts of charging. To give you a perspective, your house, you use about 5 kilowatts. So that's about almost 1,000 times more power than you would use maximum in your house. Mm-hmm. So, and in that point, even the grid wouldn't necessarily be able to handle a on-off situation like that. So they're looking at siting large energy storage next to these extreme fast charge facilities for that exact reason, to be able to kind of shave that load and allow the grid to remain stable. But
Great.
yeah, to answer your question, right now we don't have a whole lot of grid storage.
Great, thank you very much.
Mhm. So another aspect is cybersecurity. So when we plug our vehicles in, or when we plug anything in, we assume, well, it's relatively safe. Well, it seems simple that we're plugging in the vehicle. It's no different than charging our phone. But what you don't see is there's a lot of communication between the vehicle and the charger. And those chargers are all hooked into the grid and monitored, so that way the utilities can know, oh, I'm going to have this demand cycle that's coming up. I need to start spinning up more reserves, get more power available. And that leaves a door open for potential for hackers to get in there and cause issues. The scenarios can be something as simple as they can brick your car. So turn your car into just a giant brick that's completely unusable. We actually had our cybersecurity people come in and they hacked one of our chargers, and now on its little display, it continuously plays Baby Shark. Most of the time, most hackers aren't going to be so generous. And then the other one is, well, what happens if they go in there and start turning a charger on and off rapidly? It can destabilize the local grid and cause issues. So one of the areas of research that we're doing is how do we secure these from hackers? And we actually have a program where we actually take our vehicles and chargers out to universities, and in July, we're supposed to go to Michigan and have a lot of local universities in Michigan actually have their students go in and attempt to hack vehicles, hack cars through the charging infrastructure. And so we partner with Department of Energy and the car companies to see, well, is your car secure? Is your vehicle secure? Is your charger secure? Any of that. So,
Lee, we have a question from Wendy Jaquit, and it's kind of along this line. It's, would the increase in load, and it's kind of from your previous slide, would the increase in load be an incentive to make the grid safer? And maybe that has to go along with more reliable, as well as the cybersecurity that you were just talking about.
Yeah. So it goes it goes along with the cybersecurity to make it safer from that area. But there's the resiliency and reliability of the grid. So yeah, and that's a lot of work that they're doing on that other side of the lab, the microgrid and the grid simulator is, well, if we start having this type of increase in load, what happens to the grid? What can we do to actually stabilize the grid, make sure that it is more reliable and safer and stable? So yeah, there's a lot of work going between the two sides to kind of understand how does this increase in load caused by electric vehicle charging affect the grid, and how do we have to modernize that grid to be able to handle the next generation of electric vehicles.
We have another question that just came in from Clayton Cox, and he asked, do you study vehicle to grid technology for stabilization of the grid with the increase in demand?
There's been previously, yes, we did work in that. The problem is convincing car companies that we can use their batteries, or they could use anyone's battery as a grid storage device. So there is some work in that area, but a lot of car companies don't want to warranty both the vehicle's battery usage and the grid then also using the battery for a totally different application that the battery itself wasn't designed to do.
Okay, great, thank you.
Mhm. So the other aspect of our research is kind of understanding where to actually put chargers. So we've done a lot of analysis through different areas in the United States. We're actually helping the state of Montana study what it would take to create an all electric corridor between Yellowstone National Park and Glacier National Park. And where we would have to site chargers to be able to accommodate the vast majority of electric vehicle charging. We're also working with the Westmart EV project, which is Pacific Corp and Rocky Mountain Power, to be able to actually site chargers along 1,500 miles of road in Utah, Wyoming, and Idaho. And then also installing level 2 chargers within people's homes and businesses. And then it's understanding what goes into that type of research is what is the economics of the charging station? Is the charging station going to be sufficiently used to be able to justify the cost of installing the charger? Is there enough capacity in the local grid for that charger? And what level of charger do you need? How many chargers do you need? Can you get away with a handful of level 2? Or do you need to start looking at, well, do we need DC fast chargers or extreme fast chargers in that location? And as always, you can follow Idaho National Laboratory on our social media feeds through Facebook, Twitter, Instagram, or on LinkedIn. And thank you for listening. And is there any more questions that anyone would like to ask?
Come on, you guys, roll them in. We'll give them a few minutes to type and think.
Sure.
Oh, well, okay, this might be better asked later. I'm sure the battery systems are much more complex than switching rechargeable batteries in a flashlight. But would there be a way that interchangeable pre-charged batteries or units could be available so you can just leave your depleted on and pay for a new one and be on your way? Since one downside I hear is taking time for charging as you drive longer distances. It takes longer at this point until fast charging is more available and reliable. That was a question from Carol Cole.
Yeah, so there's been some exploration into the term that we use is battery swapping. So this would be you drive up to some sort of service station, they take your battery out and they put a new battery in that's already been charged for you. And then they'll recharge that one and give it to the next person. There's a couple issues that have come up with that. A lot of times the battery systems themselves are integrated into the bodies of the vehicles, so they're not easily taken out. Plus, you want to make sure that the battery is in a crash-safe zone, so it's usually contained within crash structures. So it's, again, usually difficult to get the battery out. Design issues that you'd have to have interoperability between lots of different types of cars. And to be honest, the auto manufacturers aren't always that friendly toward one another when it comes to interoperability.
Well, we got a couple more questions coming in. One from Bill Craig. He asks or states, Tesla says they anticipate a 1,000,000-mile battery, and what are your comments?
So the only area where I've seen claims for 1,000,000-mile batteries has been in the heavy-duty, medium-duty transportation area. So Tesla has a semi-truck that they're coming out with, and most of the manufacturers for those heavy-duty vehicles are looking at 1,000,000-mile lifetimes. For their vehicles, is it possible? Yeah, it's possible. I've seen some batteries that could do close to that. there's a lot of other attributes that go into, well, how long would the battery last? And so there's calendar life issues of, well, will the battery last? It can go 1,000,000 miles, but it will only last, let's say, 7 years. So if you could do 1,000,000 miles in 7 years, which most vehicles don't, then yes, it could do that. The cycling doesn't tend to be the problem. The problem tends to be more of a calendar issue of how long they sit around, at what state of charge, at what temperature. Temperature is the biggest factor in battery life degradation.
Okay, thank you. Linda Bruns asks, is INL involved in recycling batteries to reduce the environmental impact?
So we do have some programs within for battery recycling. The bigger program is actually through the Department of Energy. Actually has a larger program called the Resell program at a different national lab. We do some supportive work of that. We also have at INL a facility called the Critical Materials Institute, and that is how to actually recover and potentially even or eliminate the need for critical materials, including battery materials. So one of the more critical materials within batteries is the cobalt. It uses cobalt within the cathode, and that needs to be either recovered or we need to figure out a way to reduce the amount of cobalt. And so we've got some programs in recycling, but one of our more main focuses is actually in reduction of critical materials.
Thank you. Larry Barnes asks, in general, how does winter and the need to heat the cabin affect the frequency of charging or the distance one can go on a charge?
Sure. So it can have a significant effect. The heater within an electric vehicle is drawing energy directly from the battery. Your internal combustion engine takes waste heat from the engine to actually warm up your cabin. The electric vehicle, the electric motor doesn't generate sufficient amount of heat to actually do that. So you have to actually have resistive heaters within the car to actually warm you up, and so it just takes energy directly from the battery to do that. It can have an effect of much as decrease your range 20%. So it can have a fairly significant impact, depending upon how much you have the heater turned on, to what level, of course, how far you're driving, amongst a couple other smaller factors.
Well, thank you. Clayton Cox wants to know, what is the biggest challenge with charging at extremely high rates? Is it heat? Is it the impact on the grid, or is it something else?
So I think there's probably two areas. It's understanding the impact on the grid and actually designing a battery that can actually do that for a sustained period of time and be able to last a certain amount. So on the battery side, again, that's my area of expertise, greatest expertise is, so we have programs where we're trying to develop batteries that we can charge in 15 minutes or less, and trying to understand, well, will those make the same number of cycles as batteries that are charged at a lower rate? So one of the studies we did, and this is the data from that 2011 to 2015 experiment. We had some Nissan Leafs that were deployed to Phoenix, Arizona. And we had the people that had the vehicles, we had a group that we had do only level 2 charging, and we had a group where we only had DC fast charging, so 50 kilowatt charging. Then we also took packs from Nissan Leafs, and within my laboratory actually tested them in a laboratory environment to understand how do the effects of these different charge rates actually affect the life of the battery. And we found it actually doesn't significantly affect the battery, but definitely, as I think I mentioned before, heat and temperature are the largest factors that degrade a battery, cause degradation within the battery. But then there's also, we don't fully know what the impact of the grid is. Right now, they sell these extreme fast chargers, but no one actually makes a vehicle that you can extreme fast charge. Even that bus that I had in the picture, we only charged it at 100 kilowatts because that was the fastest we could charge it. That charger is capable of 3 times that level of charging. So,
Shelley Norman asked if you could go back one slide. And I think that's your Facebook slide.
yes.
So Shelley, do you want to go back one more slide? Or did you want to see that? That's the one.
Okay.
So I'm not sure what Shelley was looking for specifically, but just to know, I guess, that you're on Twitter and Facebook and other platforms. So
what's
let's
fun about the slide after that is that all those pictures and those 4 pictures are actually taken by INL employees out and about in Idaho.
Oh, with a hang glider in the water, and yeah. So let's see, we're at about 20 after 6. Do we have any other questions that you guys would like to ask Lee right now? And this might be a good time to also remind you or encourage you to put your feedback. I think let's just put the feedback in the questions panel. That seems to be the way that it works pretty easily. If you have any kind of feedback in terms of registration, the presentation in general, the way we ask questions, really anything. We just want to be able to do this better and have it work for everybody. And also, if you have any suggestions for topics that either the INL could bring and answer for us, or any other kind of topics that you'd like to have brought to the library. So we'll take a couple more minutes to see if we can fish out some more questions and feedback. So Lee, while we're waiting, what got you involved in electric vehicles?
So it was actually kind of by accident. I was working on my undergraduate degree at Northern Illinois and actually applied to do a co-op position at Argonne National Laboratory in the battery testing group, and that actually then turned into a full-time position for me, and I've been doing it ever since. So it's a little weird being an electrical engineer in a world of chemists. Everyone I talk to is a chemist, and so it's a lot of the stuff ends up going over my head, but I've learned quite a bit about chemistry in the past 15 years.
We have a note in the question box from Linda Bruns, who works real closely with the INL, and she says, could I recommend that you go to the INL website and check out the magazine, capital M magazine, that shares information about all the areas of research that are happening at the Idaho National Lab. So I know my father used to work at the lab, INL, and I had no idea that you folks were working on such a diverse group of projects. I'm pretty delighted to be able to bring this information and the research that you guys are working on to our community.
Yeah, it's nice to be able to work on something kind of the next forefront of technology, and kind of there's just a very strong push for electric vehicles, and it'll help everyone in the world make the world a cleaner place. It'll help reduce our dependence on fuels. And I mean, the good thing about electricity is it can come from anywhere, and anyone can generate it, and you can generate it even from the sun or the wind, and still get the same quality.
Mm-hmm. Well, and sadly, because of the pandemic, we've had some good news in that many metropolitan areas are seeing much clearer skies. And I hope that serves as an incentive for us to work harder at maintaining those clear skies in the future. And also just a reminder to everybody that this talk was brought here on behalf of Earth Week and the 50th anniversary of Earth Day. So I think that's all. Thank you all for coming. If you have any suggestions, again, for topics or any feedback for our presentations, please put it in the question bar. We'll review all that later, and we'll be sending out a link for this talk in the next few days. So thank you very much for joining us, Lee. Thank you for taking the time to Zoom in virtually, or I guess it's not Zooming, it's GoToWebinar personally, and to all the staff at the INL. So thank you and have a lovely
I think we're good, everybody.
Can we turn our webcams on?
No, I think it went really good.
Yeah, everybody's gone. The broadcast is still continuing because if I stop the broadcast, it stops everything.
I'm good. Okay, Abby, you good?
Oh, but the attendees are gone. Great job, you guys. That's wonderful.
Good job. So impressive.
Yay, Lee! Woo!
You did awesome.
Good question. Yeah. You know, and my friend Carol Cole, who is an educator, she said it might be, and we can talk about this later, Abby, but she said it might be nice to access the links that Lee mentioned, and then maybe a link to the INL magazine, and maybe there are other links that we can include in that. I'm certainly happy to do that. So
this is Nicole. Yeah, we can for sure send you the link to that magazine to send out with the recording or whatever.
okay, sounds good. Yeah. Hi, Abby.
Oh,
Hi.
great.
That was awesome. Good job.
Good, yes, woo!
Yeah, Lee, you really loosened up and talked about the slides and your knowledge, which was great without reading them. And Kristen, I love that when there weren't questions, you came up with your own. And yeah, I felt like that was great participation from the audience. We didn't even have to plant any questions. That was great.
Sure, we talked about putting a plant in there, but I was just the only reason I chatted you, Abby, was because we weren't getting any questions. I thought, well, maybe it's not working or it's not on or something, but
that was very exciting. I was trying to get Nicole to get somebody to put a
And I
question.
was starting to text someone to ask a question when the first couple came in. So yeah, I thought that was really great.
Yeah.
Thank you again, Lee, so much for your time. This was awesome.
Yes.
And
That's
I
really-
was presenter or attendees, and basically we started out with 16, and by 5:45 we had 20, and they stayed the entire time. One dropped off when the slides ended, but everyone else stayed for the whole thing. So that's a compliment to you presenters.
Yeah.
You know, and I know from doing this a long time that probably another 6 or 7 people were planning on doing it, but then, you know, Great Aunt Mary called, or the kids yelled, or, you know, or they lost track of the time and didn't want to come in part way, or, you know, there's just always those reasons. So,
Yeah.
Awesome.
or they just, like I found with the gardening class that I did a couple weeks ago, is sometimes people sign up knowing that they can't participate because they know they'll be able to get the recording and follow